Welcome to the quick video introducing Pylon, a PyTorch framework for learning with constraints. I'm Samir Singh, and along with Kareem, we'll be presenting this work that was undertaken with a bunch of folks. I encourage you to go to the website for more details. Consider neural networks that produce complex outputs, such as sequences, graphs, or even multiple tasks or variables. Now, these outputs are unlikely to be completely unrelated. Often users have knowledge about how this output is structured, which combinations are valid, how these outputs are related to each other and to the input. Existing pipelines assume that models can learn this from data. However, this is inefficient and error-prone. It is much easier to express this knowledge declaratively, but unfortunately, there is no easy way to inject this kind of knowledge into existing PyTorch codebases. Pylon aims to make this easier. So what is Pylon? Pylon is a library that extends PyTorch to allow injection of declarative knowledge. It makes it easy to express knowledge. Users can write arbitrary constraints on the output. It integrates very well with PyTorch. It requires minimal change to existing PyTorch code. And it has mechanisms for efficient training by compiling these arbitrary constraints into losses that can be efficiently optimized. Here's a quick overview of what Pylon looks like in use. Consider a usual training pipeline consisting of a model and a loss. To express the domain knowledge about the output, the user just has to write a predicate function using arbitrary PyTorch code and Python code to define which outputs are valid. So you can see this function that checks whether a specific output is valid or not. This predicate can then be included into the code base as a loss, such as by augmenting the existing loss. This converts the declarative knowledge that the user wants to express into a differentiable loss, just a single line of change. During the actual optimization, Pylon derives the gradient of this declarative knowledge as efficiently as possible, such as by compiling it into circuits or approximating it using t-norms or Monte Carlo estimation. Now, Kareem will demo some of the applications of Pylon.
Hi, everyone. My name is Kareem. I'm a PhD student at UCLA. And today I wanted to talk to you about two use cases that we implemented in Pylon. The first use case is MNIST addition. And this task is very reminiscent of the classical learning task on MNIST. However, there's a slight twist. Instead of training on single digits and their labels, we train on pairs of digits and their summation as labels. That is, our data consists of triples where the first element is the index of the first image. The second element is the index of the second image, and our ground truth is just their summation. One thing to keep in mind is that we still test on the classical MNIST test set. That is, we test on single digits and their labels. So let's step through the code. So here we can see that in cell number 3, we just defined our model, which is our MNIST net. So this is the classical MNIST net taken from the PyTorch MNIST tutorial. In cell 4, what we do is we load our MNIST image data. Again, nothing too special yet. In cell number 5, what we do is we read our MNIST addition data set. And as I mentioned, this data set consists of triples, which are just the index of the first image, the index of the second image, and their summation. And in cell number 6, what happens is that we create our model that we just defined before, and we create an optimizer for training. In cell number 7, we just create our test function. We define our test function. And as I mentioned, this test function just tests on single digits and their labels. And so what we expect is that we expect the model, even though it's trained on pairs of images, pairs of digits, and their summation, to learn to be able to identify single digits and their labels. So now we come to the meat of our example. I mentioned that more than one time that we're given pairs and their summation, but one thing that I didn't mention is that in our use case, instead of using the typical cross entropy, what we're going to do is we're going to use Pylon. We're going to define a constraint such that any predictions on two images that the network produces must sum up to their summation. And as you can see, this is defined here in lines 7 and 8 of cell number 8. It's just a simple Python function, no special syntax. And then on line 11, what we do is we create our loss. So just as you would the cross entropy loss, our enforce some constraint just becomes a loss. And then here in cell number 9, you can see that we're using this loss as you would, again, any typical loss, for instance, cross entropy in your training group. And then if we scroll down a bit, we can see that in just 7 or 8 iterations, the model converges to a 97% accuracy on the test set. So this was our first use case. Let's move on to the next use case. And here the task is Sudoku, as many of you might know it. So more precisely, what we're given is we're given a grid, a 6x6 grid with some entries filled out, as you can see here, for instance, 4, 1, 3, and other entries which are missing. And these are denoted by zeros. And what we want is we want the network to predict these entries such that the output is a valid Sudoku. And so cell 5 gives the ground truth Sudoku. So again, we create our model and we create our optimizer. And so the way to ensure that a Sudoku is valid is, as many of you might know, to ensure that the elements in every row are unique, the elements in every column are unique, and the elements in every square are unique. And so that's why we define this is unique constraint function. So given any tensor, any row, column, or flattened square, it ensures that the elements are unique. Again, here in cell number 8, what we do is we just define a loss is unique constraint in terms of our is unique function that we just defined. And then we proceed to training. So here, as I mentioned, we have 3 different types of losses. We have the row losses, which are accumulated on line 12. We have the column losses, which are accumulated on line 13. And we have the square losses, which are accumulated on line 17. And when I mean accumulated, I mean that we have the row loss. We ensure that it's unique for every row, for every column, and for every square. And here you see a bunch of code. And what that code is doing is essentially just taking a convex combination of these constraint losses. And finally, it's adding it to the cross entropy on the input entries. So on these entries that aren't 0 on X. And so if we go to the end, we now see that after training the model for 50 iterations, we get a valid Sudoku. In fact, it matches exactly the ground truth Sudoku that we're given as a label. This is further confirmed by this heat map, which shows 1 where we match the ground truth and 0 where we don't match the ground truth. And you find that all the cells here are colored in blue, which corresponds to 1. Thank you so much for watching.